In this video, I'm going to show you how to do the Tukey post hoc pairwise comparison manually and compare my calculation with the SPSS output. Let's use the same car model example in which I have 3 different car models. I want to compare whether there is a difference in their number of major repairs in the last 5 years. I already run the ANOVA test. It shows here I have 5 cars in each group, and here are the group means. And with alpha equals 0.05, I made the assumption of homogeneity variance, which means the underlying populations have the same variance. The ANOVA test shows that with the F test of 10, the p-value is 0.003, which is lower than alpha equals 0.05. So I'm going to reject the null hypothesis and come to a conclusion that there are significant differences in the number of major repairs between some of the 3 models. But the question is, I do not know which car model is different from which car model. So how do I answer that question? This is the time we're going to use post hoc pairwise comparison. Since I made the assumption of homogeneity variance and also I have equal group sizes, so the simplest test for me to run is Tukey test, Tukey post hoc test. In Tukey test, we use the Q statistic. This shows you the formula used in Tukey test. A better way to conduct this test rather than doing one pair at a time is to do this. First, let's look at the group means. And you want to copy the means and sort them from low to high. In my example, it happens to be that way. Already it's low to high. So I have 3 groups. And model 1, model 2, and model 3. I sort the means from low to high. Then I'm going to copy the means up here so that I know which pair I'm comparing to. Okay. Once I have a table like this, I'm going to first, let me just mark out the diagonal line because I don't need to compare one mean with itself. Okay, now let's look at the comparison between model 1 and model 2. Model 1 has a mean of 2, model 2 has a mean of 4. The difference between the two is simply 4 minus 2. Okay, next pair is model 3 versus model 1. And the means are 6 versus 2. So the difference between the two means is 6 minus 2. That gave you 4. And last pair we have here is model 3 versus model 2. Again, the difference is between 6 and 4. That is 2. Okay. In our example, we have 3 group means, and they have 3 possible pairwise comparison: model 1 versus model 2, model 2 versus model 3, and model 1 versus model 3. If you got 4 means, you would have 6 pairwise comparisons, so the number of comparisons increase exponentially with the number of means you have. What I have done here is simply to find out the mean differences that needed for this calculation of the Q statistic. Okay, so they doesn't matter which pair we're comparing, they share the same denominator. That's the standard error used in this Q test. In the standard error, the mean square within, or sometimes you call it mean square error, that's from this table. The mean square within right here. Okay, the mean square within is 2 in this case. and the NG, that's the group size. We know group size is 5 in our case. So we want to find out for this particular Q test, square root of the ratio between mean square within, this is right here too, over the group size, which is 5. Okay, and this 0.632 happened to be the denominator of all 3 comparisons we're doing here. So what I'm going to do next is to find out the observed Q statistic for all 3 comparisons I'm doing. So here is simply this mean difference over the standard error, and this is model 1 versus model 2. Okay, and next pair we did is model 1 versus model 3, and the mean difference, which is the numerator, is 4, and the standard error happened to be the same. Yes, it's always the same. And the last pair is model 3 versus model 2, and their mean difference is 2. So the Q observed would be the mean difference over the standard error. Okay, so remember, this is your standard error. Okay, and that's the 3 Q observed values. Remember, we have 3 Q observed values because we are doing 3 pairwise comparisons. So we're running 3 tests simultaneously by creating this Tukey table. Once we have all the observed Q values, the next thing we need to do is to find the critical Q values. So to find the critical Q, we need first to know what's our alpha value. We usually use alpha equals 0.05, and the next thing we need to know is what's the degree of freedom within in our ANOVA analysis. If you read from the table, the degree of freedom within is 12. And the last piece of information we would like to know, and we need to use it for looking up the Q critical, is how many means we're doing here. We have K level, and the K is 3 in our case. If you go to the Tukey table, use alpha equals 0.05, degree of freedom error is 12, and the number of levels, that's 3, the Q critical is 3.77. Okay, now if you compare your observed with the critical value, if the observed value is greater than critical Q value, you're going to reject the null hypothesis, which means the pair you're comparing, they have significant difference. And in our case, model 1, model 2 have a Q observed lower than the critical. Model 2 versus model 3 have Q observed lower than the critical. The only pair that have significant difference according to the Tukey pairwise comparison is model 1 versus model 3. Okay, that's the only one with a observed Q value that's greater than critical Q. We can request the post hoc pairwise comparison in SPSS as well. So I have the data in SPSS. I'm going to do the one-way ANOVA. The number of repairs is my dependent variable. Car model is my independent variable. And I always request the descriptive analysis and test homogeneous variance. To get your post hoc test, you go here, the button says post hoc, and you have a bunch of options. For now, to simplify this video, I'm going to choose Tukey and continue. Okay, here is our output. Okay, and this is the ANOVA part of the output, and here is a post hoc test. Okay, and you can see that we have the group mean differences listed here. The negative values just depends on which mean you goes first, which mean goes second. So 1 versus 2, if you go put model 1 first, it's -2. But here, if you go to model 2 versus 1, you have 2. So you have 50% of the table that's redundant information. Okay, and remember the different post hoc tests, their difference from others post hoc tests is how they choose the standard error. And in the SPSS for the Tukey test, there's a modification, so the standard error looks different than what we have in our manual calculation, the manual calculation of standard error of 0.632. That's okay. If we look at the comparison here, you are trying to compare the p-value, the significant value, with your alpha. Look at the significant value. The only pair that have significant difference, which means the p-value lower than alpha, is between model 1 and model 3. The other two pairs, model 1 versus model 2, model 2 versus model 3, they do not have significant difference. Okay? So you need to keep in mind two things. Number one, even though SPSS offer a modified version of Tukey that gave you a different value for standard errors, they should lead to exactly the same results. Okay? And the second thing you need to remember is when there's no difference between group means, they are called homogeneous subset. So model 1, model 2 has no significant difference. Those two pairs, those two means are called homogeneous subset. Model 2 versus model 3, they have no significant difference, and they are homogeneous subset.